Hello everybody. Let us start our discussion today. In the last lecture, we discussed how to solve this type of problems where we have piecewise constant potential. And at the end of the lecture, we posed a problem where the potential looks like this: Vx equals V0 for in between 0 to L, and otherwise it is 0. So it's called a potential barrier because, as you can see, this part of the potential is like a wall, and you have the electrons energy less than V0, and they are coming in from the left. So they are falling into this barrier. Some part will be reflected, some part will go inside the barrier, and as we have seen last time that in the barrier there will be exponentially decaying function, can be exponentially rising also, and as we argued that there can be some non-zero wave function in the right hand side. So there can be some transmission through the barrier, as we have discussed. So what I asked you is to calculate out what will be t in terms of the I, where I'll just remind you what t and I are. Now to start with, what we do is we define k1 square and k2 square this way. You see that k1 square is defined in both the region 1 and in the region 3, which I also called 1 because the k1 is the same. Now if you want to write the wave functions, the general wave functions, in the region 1 you have the incident and the reflected components. In the region 2 you can have both exponentially rising and exponentially decaying, and region 3 you have the transmitted components. The way you proceed to do the calculation is that you match psi x and del psi del x at two boundaries here. One boundary is at x equals to 0, other is at x equals to L. X equals to 0 you match psi 1 and psi 2, x equals to L you match psi 2 and psi 3. You see, two things you should keep in mind is that here I have taken the barrier starting from 0 and going to L. One can also define the barrier starting from minus L and going to plus L, or minus L by 2 to plus L by 2. You can work out all those problems as yourself, because obviously for every values of L we will not be able to work it out in the class. We will not work out even for these values of L, because now I have told you how to work it out. So I will try to write down the solution directly. One word of caution today: whatever I write a calculation result without doing the calculation today, it can be completely wrong. So what you should do is you should do it yourself just after the lecture and check amongst yourself. And it's a very straightforward calculation. What all we are doing is, last time remember we had I, R and T. We were writing T in terms of I or R in terms of I. Now we are writing again T in terms of I. We just have this extra layer psi 2 in between. So we know how to do the calculation, just that the calculations in this case is a little tedious. So let me directly write down the solution. Remember that we were hunting behind the transmission coefficient, which was given by this, which is essentially T mod square, which is T star T by I mod square, I star I. So if you calculate out the transmission coefficient for this, okay, so before we go further, let me tell you that this type of problem is called potential barrier problem, and as you will see that there is something expected here. It's also called tunneling problem. Now why it is called a tunneling problem? It is because if you have a classical particle, you know that it will not be able to go past the barrier. You know that for a rocket to be sent to this out of the Earth's orbit, you need to give it at least 11.2 kilometer per second velocity. That is the kinetic energy, that's E, that has to match with the gravitational potential energy offered by the Earth. So your rocket has to go away of the Earth's pull. Similarly here, not though exactly same, but similar here, that this electron which has an energy E doesn't have enough energy apparently to go over V0. So it has to somehow go over V0 to come into the right hand side. But in quantum mechanics, what happens is even if it doesn't have that much of energy, sometimes it is found in the right hand side. This is actually a property of the wave, and for light wave, Acharya Jagadish Chandra Bose has shown this to happen in the early 1900s. But it also happens for electrons, and as we'll see that it happens for many other subatomic particles, and we'll discuss those at the end. So let me write down this transmission probability. This is equals 1 by 1 plus. Let me write things in a little symbolic way here, and then I will tell you what they are. Okay. So I have written two quantities which are unknown to you. So let me first introduce them. So gamma is V0 square by 4 E naught V0 minus E. Okay. So it only depends on V0, and you can see it's a dimensionless quantity. Alpha is also a dimensionless quantity. It is simply K2 times L. And let me still remind you what is K2. Alpha is also a dimensionless quantity. It is K2 times L. So K2, if you remember, can be written in terms of the other things. So this is this. And I recognize that you may not be familiar with this function called sine hyperbolic. Sine hyperbolic x equals e to the x minus e to the minus x by 2. So as you may recognize that we'll use this shortly, x very greater than 1, then sine hyperbolic x, you see there are two terms, e to the power x and e to the minus x. If x is very large, say goes to infinity, e to the minus x will go to 0 and e to the x will rise up. So this will essentially be e to the x by 2. And in the opposite case, if this is much less than 1, then what will happen? Then we have to expand e to the x. So let me write sine hyperbolic x here. This will be half, but then e to the x is 1 plus x, and e to the minus x is 1 minus x. So if it is small, x is small, then I don't need to keep the terms further. So this is just equals x. So this is just about sine hyperbolic x. Remember, square of that sits here. So this is the probability of tunneling. A tunneling coefficient. This essentially, what is it telling you? It is telling you, given this much of incident, how much will be tunneled. So it is essentially the probability of tunneling. Okay. So let us consider two cases, two extreme cases, which involves the value of x here and here. So let's say case 1. Say V0 is much greater than E and alpha much greater than 1. So alpha much greater than 1 corresponds to x much greater than 1. So then I will just get e to the x by 2 as sine hyperbolic x. So I will, this sine hyperbolic square alpha, what will it become? So sine hyperbolic square alpha, sine hyperbolic alpha square will become 1 by 4 e to the 2 alpha, just because I am square. And V0 is much greater than E. So in the gamma expression, in the denominator, V0 minus E I can write as V0. So the gamma becomes, gamma is, let me do it once for you, V0 square by 4E V0 minus E. So this becomes, V0 is much greater than E, so I can forget E. So one V0 cancels out. So this is just V0 by 4E. So what happens to T? So T is 1 by 1 plus gamma, which is V0 by 4E, into sine hyperbolic square alpha, which is 1 by 4 e to the 2 alpha. And remember, alpha is k perpendicular, k2 times L. And now see, this is, if alpha is very large, obviously e to the alpha is enormously large compared to 1, and V0 is also very large. So this number is also very large compared to 1. So this 1 I can forget. So this T just becomes, so T in this case just becomes 16E. Only this term survives, and I can take it to the numerator. 16E by V0 e to the power minus 2 K2L. Okay. Let's take a real life example for this. Let's say that, okay, we have found that there is a probability of tunneling. There is a probability of finding an electron in the right hand side here in case of quantum mechanics. That's why it's called tunneling. Tunnel, you know that you have this barrier is like a door, or if you wish, a mountain. Tunnel is like you have make a tunnel through the mountain and you reach the other side without going through the top of the mountain. So there is a probability of finding the electron in the other side, but we know that if we have to go from one room to the other and there is a wall in between, we have to go through the door. We just cannot go through the walls of the room. We cannot just pass through every mountain at our wish. So what is happening? So maybe that in classical mechanics, this tunneling probability is very less. Okay, maybe that it is very less, because of that we are not being able to tunnel through the walls. So let's ask the question that what is the probability, what is T? So for that we consider a classical system, and it's like you can, if you wish, can say that, okay, so the V0 in this case I will classical mechanics, so it's measure in terms of joules. So it is a 16 joule. E is say 1 joule, and we can take for approximation E much greater than, or much lesser than V0, which is the approximation that we have just taken, and say we have a mass of 2 kg ball which has a mass of 2 kg, and my wall has a width of 1 meter. Okay. So you ask the question, and that what is the tunneling probability? Now, first of all, we have to check if alpha is greater than 1 or less than 1. So let's calculate alpha. So alpha is L by h cross root over of 2m v0 minus e. So because v0 is have already taken much greater than e, so let's call 2m v0. Okay, so this is approximately. So let's see what we get. L is 1 meter. H cross is 6.6 into 10 to the minus 34. And inside the square root, I have 2 into 2 into 16. V0 is 16. So that will give me 8. So 8 by 6.6 into 10 to the 34. Enormously large. So if I say alpha much greater than 1, that's an understatement. Alpha is much greater than 1. So we can happily use this approximation. So my t will be 16e by v0 e to the minus 2k 16e by. So t in this case is 16, e is 1 by v0 is again 16, so that's just 1 e to the what is there, e to the minus 2 alpha. So minus 16 by 6.6, it really doesn't matter, still I'm writing minus 34, sorry, plus 34. You see, e to the power 10 to the 34 or 35, that is essentially 0. So that is all approximation, this is 0. So you see the tunneling probability is, okay, so to be strict, it is not exactly 0. There is a very small tunneling probability, but it's so small that you need to wait for a time which is more than the age of the universe. So it's not practical. Okay. So let us consider another physical example. And this is what could not be explained before the advent of quantum mechanics. And George Gamow was the first person to realize that it is the quantum mechanical tunneling which can explain this phenomenon. So let me tell you what is the phenomena that we are looking at. So we know that, so if I consider, say for example, some uranium nucleus, there are all this, it's not necessarily have to be uranium nucleus. That's what came into my mind. So it has these protons and neutrons all very closely packed, right? Some nucleus. And the size of the nucleus is enormously small, say 10 to the minus 15 meter. Okay. So the first question that arose is that in this very small size, all protons has positive energies. So how is it that all protons has positive charge, and the positive charges will repel? So how is it that everything is so closely packed? So one theory came about which said that there is, in addition to the electrostatic potential or electrostatic force, which is q1 q2 by r square, there is also some other force. So this electrostatic force is a repulsive force. So this is repulsive and this is attractive. That holds these nucleus together. This nucleon. So these proton neutrons are called nucleon. So these nucleons together. Now it's an attractive force. An attractive force always need to have a negative potential. So one potential that was suggested for such a system looks like this. So what I'm plotting here is the distance from the nucleus, let's say the center of the nucleus if you wish, and this is the potential. And the potential looks like this. Okay, so what is the idea? The idea is that if the electron has some energy, say here, so say this tip is about say, okay, so these numbers are not exact, but say 25 MeV, and the nucleons, they have lesser energy than 25 MeV, so they stay inside. Okay, so if the nucleons have, some nucleons say have 5 MeV, so then we know that it will not be able to come out. So this was the initial theory, but then what was observed is alpha decay. So alpha particle is 2 protons and 2 neutrons. So it has like 2 positive charge. So when alpha decay is observed, it was sure that somehow these particles which are staying inside this potential well here, which was known to have lesser energy, comes out from the nucleus. So George Gamow modeled it in the following way. He said that, okay, so this can be seen as a potential barrier, just you are looking at in our problem, and maybe it is a quantum mechanical tunneling phenomena that's happening. So we will not be able to do a complicated analysis where I need to consider this very complicated shaped potential. What we can do is we can say, okay, so let's see what happens. We assume, and we are not doing potential of like a nucleus, which is a spherically symmetric, more three-dimensional potential. We are doing one-dimensional potential, but why not we apply in a toy model of nucleus in one dimension? Toy model means that it does not replicate the exact situation, but we will be able to understand the physics. So say the top, this is still say 25 MeV, and the energy of the alpha particles which are falling into this barrier from the left are like 5 MeV. And as we said that the dimension of the nucleus is about 10 to the minus 15 meter. Okay, and what is the mass of one alpha particle? So it has 2 protons and 2 neutrons. Neutron and proton has almost the same mass, 1.67 into 10 to the minus 27 kg. So I can just now treat it as the same tunneling problem that we were looking at earlier and ask the question, what is the probability of transmission? What is the probability of transmission? Okay, so to do that, first we calculate K2L. Now I will not redo the calculation again. It is just instead of using the values here, I have to now use the values there. So let me still write down what are the values that I will have to provide. So K2 is L by H cross. L is now 10 to the minus 15. H cross is of course H cross. And then I have many different things. I have 2, I have m, which is 4 into 1.67 into 10 to the minus 27, and I have E. Now the E minus V0 is 20, but it's in mega electron volt, so I have to convert it into joule, which is first 10 to the 6 to go from mega to electron volt into 1.6 10 to the minus 19. Now if you do work out all this, you will get something nearly 0.3. Okay, so again, I do not swear by these numbers. You should do by yourself and check what you get. So which means, and let us calculate again what is gamma. Gamma is written here. Let me show you once more. Gamma is V0 squared by 4 E naught V naught minus E. So V0 is 25, so it's 25 squared by 4 E naught into V naught minus E, which is 20. So this goes away, 125 goes away, this is 25 by 16. So now if you calculate T, this is 1 by 1 plus gamma 25 by 16 times sine hyperbolic square 0.3. Okay. So I'll request you to complete the calculation, put these values in your favorite calculator and figure out what is this number. So what is this telling you is that if there is one electron that falls into the barrier, how many electron will be going into the other side? Sorry, not electron, but alpha particles. So if there are 100 in the one side, how many will be available in the other side? But let us ask the question. So this is what fraction of alpha particles will be tunneling through? This is the question that you are asking. Okay, so now let us say that we have a nucleus and we have the nucleus which has atomic number A. Okay, so that means that it has A protons plus neutrons. So it has A nucleons, essentially, A number of nucleons. It can be proton or neutron, doesn't matter, but total A. Okay, so fraction of the nucleons for alpha particles. So it's obvious that all the nucleons doesn't make alpha particles and come out. You can assume that some fraction f alpha makes alpha particles. So this is A f alpha is the number of alpha particles. So this you can assume as the number of alpha particles. Alpha particles in the nucleus. Okay, so there are a lot of simplification going on. Nothing happens exactly like this, but we will have some understanding of what we call the radiation or radioactivity of a nucleus. So you know that when there is an atomic bomb blast, there is some radioactivity that goes on for decades to come. there are sources, radioactive sources, which are very harmful for our body, and sometimes they're also used for healing things like cancers and all. So we are trying to figure out that how much will be the radioactivity for such tunneling of alpha particles. So what we said is that we figured out that if there is one alpha particle falling into it, or what is a fraction of alpha particle that will undergo tunneling for in such very simple model. And then we figured out what is the number of alpha particle in a nucleus which has A atoms. Now you have to ask the question that how many of these nucleus will be there. So if I have m gram or m kg of this substance, the number of alpha particles inside, how do I calculate it? For 1 it is A times F alpha. So if I have m kg, then roughly each of these atoms, because they have a number of nucleons, they will weigh mp times A. mp is the mass of a proton, times mass of proton is same as mass of neutrons. So their weight will be mass of proton times A. So if I have m gram of this substance, this is the fraction, this is the number of such nucleus. This is the number of nucleus. So this is number of nucleus in the m gram of this substance. Each nucleus will give you A times F alpha times alpha particle. So A cancels out, but this is essentially the number. So number of transition for one for these alpha particles hitting the barrier once, so this will be m by mp F alpha times my transition probability. So these are the number of alpha particles falling into the barrier, and then transition probability, you find the alpha particle outside the nucleus. And why did I say that hitting the barrier once? Because you see, this is essentially, if I just think about the nucleus is not like one barrier in one side. The actual picture, little more realistic picture will be, there will be two barriers, because the nucleus is like spherically symmetric kind of thing. So you can think of you are surrounded by the walls in all the sides, right? So what, because you are want to go out, you as an alpha particle want to go out, you are hitting the barriers in both the sides many times. Okay. So for one such hit, this is the number of particles that will come out. But we can also ask the question, roughly speaking, what will be the number of hits? So what is the number of hits per second, obviously? How do I calculate it? Well, I use the uncertainty principle. I say that the electrons has energy E. Okay. So if the electrons has, sorry, not the electrons, the alpha particles has energy E. So I say that they have an energy uncertainty delta E, which is of the order of the energy of the alpha particle itself. So this is like 1 MeV. So remember that our alpha particles, we said, have 5 MeV. So you can take 5 MeV also. So, but it doesn't matter really. Exactly, I will not get an exact number, but say 1 MeV. And then, if the amount of time it spends inside this barrier is delta t, the uncertainty in that time is delta t, so then this is h cross. So I can figure out what is the amount of time it spends in between the two walls. So that delta t is h cross by delta e. So number of hits per second roughly goes as 1 by delta t, which is delta e by h cross. So we can now figure out number of alpha particles coming out of the nucleus per second. What will be this number? So for one hit, this was the number m by mp f alpha t. So one hit m by mp f alpha t. Per unit time, the number of hits is delta E by h cross. So this is the total number of alpha particles that you will see to come out per unit time. Well, obviously there are a lot of assumptions gone in here and all the numbers are rough, but you can still figure out what is the order of these numbers. So I request you to use, so some of these I have already told you. So you use say f alpha equals say 0.5, m for 1 milligram, and everything else is already known to you. So figure out what is this. So delta E you can take 1 MeV. Okay. So there is a unit for number of disintegration per second but after Madame Curie. It's called 1 Curie, and you can figure out what is the unit. So find in terms of, you will see that the unit is very small, terms of microcurie. Okay. I'm not telling you exactly how much is 1 curie because you can always go to Google and search for it. You will get it. Now, this is a natural phenomena which could be explained, and when Gamow actually calculated it more precisely, obviously, he could explain how much alpha particle should come out from different nucleus, and it matched with the observations. But we also can use this phenomenon, and people have devised way of using this phenomena, tunneling, to make microscopes. And there are several microscopes, so which based on tunneling. I will talk about the very basic scanning tunneling microscope. You see, the purpose of today's lecture is not to show you how to do calculations, which we have already done, but to tell you that these calculations are not just for academic interest. It is also that we can explain certain phenomena we have seen, and we can design certain instruments. What is it for? What is scanning tunneling microscope for? Imagine that I ask you to measure the thickness of this glass or the upper surface of the glass. I ask you to make a photograph. The glass is the glass in which I am writing, or the glass in which you are trying to look at your screen, that glass. Now the thickness of that glass very tiny, very small, say 100 nanometer from place to place. obviously a proper, if I use a normal scale, I will not be able to measure it. I need a kind of microscope, but when it comes to few nanometers, microscopes are also of not much use. When people figured out using tunneling, one can design a microscope which will be able to figure out small undulations in these surfaces. And it is used very widely. You will find several scanning tunneling microscopes in our department as well as in the institute in different departments. So the problem is this, that I have some slab, and it is, you can imagine it's 2D. I am just drawing in one dimension. And I want to measure this ups and downs in the slab, and those ups and downs are very, 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 very tiny. So what is done is the following. So you put a metal tip here, and again, so what I am drawing will, if you look at the instrument, will not look anywhere near similar, and the actual operation will be also a lot more complicated. What we are trying to do is just to guess out uh, the principle behind it. I will even not say theory, because that is again complicated, and different ways you can do this. So what I do is this is usually called sample, which is the thing of which you want to measure the thickness. And I do a connection from the sample to ground. So ground it means that if there is, the voltage of the sample will be zero essentially. And then you apply a uh, voltage here to this metal tip, and there you have, so what I am drawing here is like an arrow. It's called a amplifier. This is a very tiny current that I want to measure, so I amplify the current, and then I put an ammeter here and I measure that current. So this is approximately the setup. So let me tell you what is happening, what is that we are trying to do. You see, if the tip touches the sample, then there will be a current. Everybody knows that there will be a current if the tip touches the sample. There is a tiny voltage difference that will happen, because there is tiny resistance between where I have put the wire up to the this is the probe wire. So where I have put the probe wire, so this is the probe wire. Depending on that, there will be a tiny voltage difference between that and the sample and the ground, and I will be able to measure something. But I can be more clever. So what I can do is, I can keep this tip a little higher, as I have shown here, which is not touching the sample. Now what does it mean? It means that I am not completing the circuit, right? If I have touched the sample, I would have completed the circuit, but here I am not completing the circuit. And you know that if the circuit is not complete, means that your switch is in off position, there is no current. So what will I do then? Well, there comes the tunneling thing, that you imagine that the sample has a lot of electrons, and your tip also has a lot of electrons. And because you have given it a voltage, so that electrons are also agitated, so they have certain energy. So this is the age of the, so imagine that this axis is x. So this axis is x, and this is the age of the probe, and this is the age of the sample. Okay, age of the sample is not quite constant like this, but I've just drawn it. Now the electrons has certain energy here, can have certain energy here. The electrons usually cannot be found in between. That is why we say the switch is off. But if this gap is very small, this like just our potential barrier. So this there will be some potential difference. Sorry, some potential height of this barrier, which is V0 is greater than E, and that's why the electron is not going past the barrier. But if the gap is narrower, probably we'll be able to make the electron pass through the barrier. And that is what is done in scanning tunneling microscope. So for example, so let's say that V0 is like 6 electron volt. Why I say 6 electron volt? Because usually it's measured in volts. So and then one, it's the electron which is passing through, so you'll get 6 electron volts. E is about 1 electron volt, and the thing that is passing through is electron, obviously. And L is how much should you want to take? Say 2 nanometer, etc. Okay, so if you calculate, you will see that in this case, so what I have to do now, I have to calculate what is alpha. So please do that. I am not doing it. Calculate what is alpha, and then we will see that should I use the full formula that we have written down here, or can I do certain approximation? You will see that this approximation in case 1 that we did, and the other case we did not do any approximation. So this will work very well. So I get the tunneling probability as 16E by V0 Okay. All right. Now, why is the probability, tunneling probability important here? Well, tunneling probability gives you how many electrons will pass through the barrier, and that will give rise to this current. If the electron pass through this barrier, you get certain current here. And once I know what is this current, then I can measure the current, and from that I can figure out how much is the distance of this undulations of the sample from the tip. Now the tip stays at the same height, and you move the sample, and as you move the sample, you essentially scan the sample. That's why it's called a scanning microscope. So now L can change. So if I change L by dl, then T changes by dt. So dt will be, everything else remains same, minus 2k2. So if L increases, obviously tunneling will reduce the tunneling probability. So that we can see from here, if L increases, the tunneling probability will reduce, right, e to the minus L we have in there. So if I calculate dt by t, I should write dl over here. If I calculate dt by t, then this is just minus 2k2 dl, and this will be proportional to the current that I see in my probe. So dt by t will also give me fractional change in current. So say delta I by I. This is fractional change in current. And what will that be? K into delta L. So I can calculate delta L, which is the undulation that I want to measure, as 1 by 2k 2 delta I by I. You can put a minus sign over here, but it's really a convention which direction you call plus. But this is the basic of the scanner tunneling microscope. Looking at the change in the current with respect to the initial applied current, I can figure out how much is the undulation in the surface. Okay, so we have come to the end of the PHY-101 course. Let me ask you to think about something which I thought that I will tell you. Look at this formula, stare at this formula for the tunneling probability, and ask yourself the question, what affects the tunneling probability? One thing is obvious, that alpha affects the tunneling probability, and alpha is proportional to L. Like for example, here we can see that it is proportional to L. What else affects the tunneling probability? You will see the other important thing that affects the tunneling probability is V0. Now I showed you certain graphs last time. Try to learn how to draw graphs and try to plot this t as a function of L, choosing some suitable values of EV0 and K2, and try to see how it looks like in this approximation as well as in the full form. How does t changes, small t changes in terms of capital L and V0. This is just for your understanding. So we have seen today how to use quantum mechanical tunneling to make a device to explain certain things that happens in the nucleus or the alpha decay, and why it cannot be used to tunnel through the walls of our home. I hope you enjoyed this course. This was the last lecture. Thank you.